Good morning, everyone. Welcome to today's speech about deep learnings and cognitive modelings. Over the past couple years in Princess Margaret Cancer Hospitals, we have been trying to model cognitive intelligence and to predict the cognitive development of pediatric patients after they receive cancer treatments. In this speech, I'm going to share some of the insight we learned over the years. I will first introduce the problem and then go over the solutions and the methods we use to tackle the problems, and then ending the presentation with some takeaways and impacts about the significance of our projects. So why is modeling intelligence important? Well, the project first started with where we tried to figure out a way to spare children from further cognitive decline after they receive brain cancer treatments. And then we realized, as things progress, we probably should ask the right question first. Some of you probably experience asking the correct question is crucial. So we asked ourselves, what is intelligence? And how can we teach a model to understand human intelligence? And then developed predictive and descriptive methods to predict and maybe to foresee the cognitive developments of those children and potentially spare them from cognitive decline and avoid risky treatments. The first half of the question is easy answer. What is intelligence? We have the standardized Welsh score to base on, which is commonly known as the IQ score. So we use that as our cognitive markers to label the data, which is one of the many cognitive definitions we used. And the focus for today's topic will be on how we model it. So the second half of the question. And as always, to do any kind of modelings, you have labels on your left-hand side, which is the IQ labels. And on the right-hand side, depend on how you structure the models. It can be a function, a functional, or a backup models to influence your IQ labels conditional upon the model parameters and your brain structures. So model parameters here is theta. In this brain image, you can see there are like a couple regions highlighted. Those are the regions that were once suspected to be responsible for intelligence development. Only 3 were confirmed so far. And because due to the complexity of the data and modeling, it has been very difficult to map the physiological biostructure to the intelligence. One of the many challenges is that conventional regression models cannot really answer how does additional dimensions change your trained parameters. For example, you change something on, let's just say, a 2D space, and what if I add additional dimensions into your data? Does that change your descriptor of a variance? And how does it change your descriptors, and by how much? So conventional methods cannot really answer that. And there are also some other limitations. For example, they rely too much on low-dimensional data set. Oftentimes, it's oversimplified. So far, I saw data that use models that use a dozen parameters that try to predict what intelligence or the inference is like. And those statistical models are not adaptive and scalable, not to mention interpretable. So the solution we propose is to scale up the data. So we use very high dimensional data set and train the models on roughly around 600 billion numbers of variables. And then we build an ensemble methods, which can include a bag of classical machine learning models and some more complicated machine learning models in our software layers. And after the software layers tested, we deployed it onto dedicated infrastructure layers. Here are some of the methods we use. First, we pre-train the models and establish some benchmarks so that we can see what's the least best performance score we can achieve. And after that, building on top of those benchmarking models, we move on to more complicated automated learning, which based on deep net morphism. And then knowing some of the learned descriptors, we have Bayesian inference to draw descriptive interpretation. This will let us to take advantage of the inference nature that Bayesian models can offer. And if all the software pass our internal test, then we can deploy it onto the hardware and do hardware optimization. One of the highlights is memory compression. We'll go over that later. Okay, without further ado, let's see some benchmarking results. The color bar here shows different performance scores of models trained on different kind of brain features. And overall, the training and testing score can reach roughly above 70 percentiles, which is not too bad. But why don't we try to boost the performance score a little bit to see how far we can go? Here's where the deep net morphism comes in. We use an automated learning algorithms to construct neural networks. For example, let's just say you have an initialized neural network start with NA neural architecture, and it can morph into an NB architecture. Let's just say you start with an initialized architecture has 9 layers. So to morph into the new architecture, which has 10 layers, you can just add additional 1 layers to the 9 layers architecture. This kind of technique benefits the overall computation significantly because all the previous trained parameters no longer need to be retrained. So parameters compute in those 9 layers can now move to the new 10 layers network. So only the parameters of the additional 1 layers need to be computed. And this kind of computational benefit passed down through the neural network as well. As you can see, it's highly efficient. So we no longer need to compute any trained parameters as what currently the industry has been doing. And in the training phase, we do selective penalty functions. So depending on the cost functions, we do different kind of penalties and regularizations. If you compare the score with the DeepNet versus the best benchmarking in sample methods, you can see that we did have some performance gain, so boosting from 78% to 93%. After all the trainings, we're able to obtain a fully trained deep neural net. And from top to bottom here, consists around 200 neural layers. And none of those layers are manually designed. So all of the architecture are automated. But there's a problem though. We don't really know if the model parameters are generalized. So if we want to obtain and train a generalized model, we first need to add like 2 more ingredients into our modelings: a probabilistic distribution and a latent space. Basically, we think that the common sense or the classical MAT or MLE machine learnings are not sufficient enough because they all do point estimations. Hence why we pick Bayesian methods, which do gradients and distributions of the estimators during the training. So in the Bayesian descriptive learnings, we pick variational-based inference. I will go over the reasons behind it and how we model it. And then in the results section, you will see that how it can capture the latent distribution and the model uncertainty. So in this variational-based inference, the reason why we pick it is because it resembles Monte Carlo micro-strain model. And this kind of a resemblance reminded of one of the current base standard that being used in the industry. MCMC and variational inference are the 2 most used approximation methods. And we need an approximation methods to approximate the latent distribution. So far, only variational inference use explicit parametric approach. It can not only scale to very large data set, but also compute the latent parameters distribution quickly. So we picked a variational inference. In this equation, just for example, let's just say you want to model your data distribution, which is the probability of your X. And for our case, it's brain features. It can be formulated into an integration of your conditional probability of your data on the parameters and multiply by the posteriors. The posterior here is the model parameters conditional upon your brain features and your IQ labels. So the focus will be on posteriors because the first term is not too hard to get. Posterior here plays a crucial role in descriptive modeling. So now the problem becomes, how do we solve this posterior? By use-based learning, posterior can be expanded into two terms, normalization term and denormalization term. However, though, the denominator acts as a normalization term and it is intractable. Basically, we cannot solve it computationally. So if we can find a way to put this intractable term inside an expectation function, so this integration can just magically disappear. Luckily enough, we found KL divergence, which provided us the exact expectation calculations we need. So in KL divergence, all we need to do is just to run optimizations by minimizing the divergence between the Q function and the posteriors. And after some math operations, these cost functions can just be condensed into three simple terms. There are also a couple properties in this Q function I want to go over. First, it represents our latent distribution. It should be fully factorized so that it can be parameterized into a functional as the variational parameters. So we use this Q function basically to approximate the unknown posteriors. I kind of want to reiterate here the beauty of doing optimization on this KL divergence. Computationally speaking, it transforms an integrations of a joint distribution. So any kind of joint distribution, it can be the joint distribution between your data or the joint distribution between your labels and your data. And it can transform such integrations into an expectation function, where we no longer need to concern about the intractable term. So in the result, I'm going to highlight how we are able to capture the latent distribution and model uncertainty. So let's just focus on the upper true graph. The upper true graph is your mean distributions of your parameters for each individual features. So exactly the same as what you get in MLE or MLP machine learnings. Nothing different here. The bottom two graphs are the variance of your parameter distributions, which are not normally gained through the MLE or MLP machine learning models. So in the specific section highlighted here in green, those are the parameters for the left temporal lobe of the brain. So through here, we can see that there are a couple patterns we observe. So on the left-hand side, two images are response for the classification of a class 1, and the other side of the image are for class 2. So this kind of brain regions, it didn't tell us much. Like we know that like some pattern of mean distributions can give us some kind of predictors, but it's the variance distribution here are interesting. And we find that because the variance did not fluctuate too much, so we can rely on this variance distribution, and we accept it as clinically the acceptable range, so that now we can finally probabilistically conclude that this section of the features, which is the left temporal lobe, if we have parameter changes regarding to this model, regarding to these features, it will actually cause intelligence fluctuations. So we can draw the conclusion here now. And now we finished all the software development and moving on to some hardware optimization. We did some memory compressions on chip as well. I was told not to share the algorithm publicly, so if you're interested in knowing more about memory compression, you can talk to me after the presentation. But I can show some results from the optimization. So before the compressions, the memories has been climbing and reached around 75 gigabytes per node. And after compression, we can cut it down to 25 gigabytes per node. So from 76 gigabytes to 24 gigabytes, which is not too bad. This kind of computational efficiency directly translates into capital and operation spendings, which means 3x save on the spending. And after factoring into our other computing costs and electricity, we find that we can achieve at least around 60% more expense savings. So more funding can be reallocated into our R&D and operations. Now moving on to deployments, one of the methods we use is GPU direct RDMA. Basically, it allows us to find a shortcut to retrieving the data. If your GPU wants to retrieve data, it no longer needs to go through the system memory and your CPU. So data can be directly transferred from your data storage to your GPU. So again, it's highly efficient. Some takeaway for today's presentation. This is the first time we are able to model not only the latent variables, but also the uncertainty of the latent variables of the brain, so that we can finally model latent intelligence. And some of the models we build in the benchmarkings, they have some predictive capabilities. And in the Bayesian model, you see they have descriptive capabilities. Since we did software optimization and hardware optimization, all these trainings is highly efficient. And again, from the Bayesian model, we learned that the predictions is now probabilistically accurate. So we no longer need to just rely on, for example, just like cross validations and seeing the variance from there. So knowing all of this, how can we apply the model to the industry? I think it really depends how you structure your questions. If you're interested in modeling uncertainty and knowing how the descriptors fluctuates, this kind of methods would be highly beneficial for those kind of projects. Last, let's go over some of the impact our work has. So this kind of infrastructure is highly scalable. It supports multi-threading and multiprocessing. So we can parallelize our trainings. And I have shown that the model uncertainty can now be trained. So we can finally answer the questions such as, how certain are we at the prediction rate? And if the descriptor fluctuates, how much of it fluctuates? Can we trust those descriptors? And by doing this kind of Bayesian learning, we can encode and compress information efficiently. On the interpretable side, it condenses information that are only essentials to the predictions, as you can see from the Bayesian result. So now we know which features significantly contribute to the predictions. Basically, no more black box training now. On the budget and ESG side, I showed that we can roughly reach around 3x capital and operation spending save. And because computing resources are cut down now, so heat and electricity are reduced. That concludes my presentation. Thank you.